Welcome to the Explainer. We're just flooded with data everywhere we look. So how do we find the real story in all that? Well, today we're going to dive into a really powerful technique called kernel smoothing. It's all about helping us see that clear signal that's hiding inside all the noise.
All right, so let's just jump right in. Take a look at this plot. It's showing age versus income. When you first see a cloud of data points like this, the real story, it's not obvious at all, right? It's just a messy scatter of dots.
So that's the big question, isn't it? How do we find the actual trend that's buried in all of that mess? The real challenge here is to separate what's meaningful, what we call the signal, from all those random ups and downs, which is just noise.
And that right there is where this idea of smoothing comes in. It's a whole set of techniques designed to do exactly that, to pull out trends from noisy data. And what's really cool is, it's super useful when we don't even know what the shape of the trend is supposed to look like beforehand. Okay, so where do we start? Let's begin with the most straightforward approach, something you've probably seen before if you've ever looked at a histogram or a moving average. We're just going to call it the bin. This first method is called bin smoothing, and it's one of the oldest tricks in the book. The idea is simple. You just chop your data up into these little intervals, or bins. Then, for each bin, you just average all the points inside it. As you kind of slide that bin along the data, calculating the average as you go, you start to connect the dots and a trend line appears. But there's a problem. While it's a decent first step, this method has a big flaw. Because you're just taking a simple average, the line you get is often really jagged and wiggly. It's not smooth at all. And even worse, it's super sensitive to where you decide to place those bin boundaries.
So clearly we need something better. How can we improve on this? Well, this leads us to a much more elegant and, frankly, more powerful solution: kernels. Here's the big idea, the key insight. What if, instead of treating every single point in our little window equally, we move to a weighted average? The idea is, let's give more importance, more weight to the data points that are closest to the spot we're looking at. And how do we do that? We use something called a kernel. Now, don't let the fancy name throw you off. A kernel is really just a weighting function. The easiest way to think about it is like a little smooth, symmetric bump that we put over each data point. It basically lets that point's influence spread out to its neighbors.
And wow, just look at the difference this makes. Instead of that clunky rectangular box from the bin method, we're now using a smooth shape like this Gaussian or bell curve as our kernel. We're basically putting one of these little smooth bumps over every data point and then adding up all their influences. The result? A much, much smoother and more believable trend line.
Okay, so this is obviously a huge improvement, but it's not quite magic. Using kernels means we have to make a couple of really critical choices. So let's break down what those two big choices are.
All right, choice number one. And this is by far the single most important parameter you have to set. It's called the bandwidth, usually written as just h. Think of it as a scaling factor that controls how wide or narrow our little kernel bumps are. The best analogy, it's like the focus ring on a camera. It's going to determine how blurry or how sharp our final picture, our trend line, is going to be.
So let's see this in action. What happens if we get the bandwidth wrong? Well, if we make the bandwidth too wide, our picture becomes totally blurry. This is called oversmoothing. Sure, we've gotten rid of the noise, but we've also completely washed out the important details of the trend itself.
Okay, now let's start dialing that focus in. As we narrow the bandwidth, the picture gets sharper, right? Suddenly, the underlying structure of the data starts to pop. See? That's looking a whole lot better.
But what if we go too far? If we make that bandwidth too narrow, we run into the opposite problem: undersmoothing. Now our picture is too sharp. We're not really finding the trend anymore. We're basically just playing connect the dots with the random noise. We've lost the signal all over again.
So you can see, choosing the right bandwidth is a total Goldilocks problem. You can't be too wide because that gives you high bias. You're hiding the real story. But you can't be too narrow either because that gives you high variance. You're just chasing the noise. You have to find that sweet spot that is just right.
All right, so that's bandwidth. Super, super important. Now, what's the second big choice we have to make? Well, it's the actual shape of our kernel, the weighting function itself. And as you can see, we've got a few different options to pick from. So we've got a few different shapes here. There's the uniform, which is basically that box we started with. Then there's triangular, biweight, and the normal or Gaussian kernel we saw earlier. But here's what's so fascinating, and maybe a little surprising.
when you actually compare their statistical efficiency, they're all almost identical. The differences are just tiny.
And that brings us to what is maybe the single most important lesson for anyone who actually wants to use this stuff. This quote really says it all. The choice of kernel is not as important as the choice of bandwidth. Honestly, if you get the bandwidth right, you've won 99% of the battle.
Now, for all you perfectionists out there who want the absolute technically best option, there is a winner. It's called the Epinechnikov kernel. It's been mathematically proven to be the most statistically efficient, the optimal choice. But, and this is a big but, in the real world, the difference between using this one and, say, the much more common Gaussian kernel, it's almost always negligible. You'd barely notice. So, okay, we've spent all this time learning how to draw these nice, smooth lines through a bunch of dots. The big question is, why should you care? Why does any of this actually matter?
Well, it matters because this fundamental idea is used everywhere. Seriously, from finding economic trends, to estimating probabilities in machine learning, to processing signals and reducing noise, to visualizing really complex scientific data. I mean, think back to that first chart of age and income. Smoothing could tell us the real story of how income changes over a lifetime and pinpoint exactly when it peaks. The applications are just endless.
At the end of the day, that's what kernel smoothing is. It's this foundational tool for finding the signal in a world that is just full of noise. It lets us look past all the random chaos and actually see the underlying patterns, the true functions that are driving what's going on.
And that kind of leaves us with one last question to think about. In this age of just endless data, what hidden stories, what crucial signals are out there right now just waiting for someone, maybe you, to find them? All it takes is the right lens and, of course, the right bandwidth to bring them into perfect focus.